It is in the second part. We have already seen in the first part of video that why does this protein have native to intermediate and intermediate to some unfolded conformation, and the data was fit with that kind of thing. And also the kinetics was measured. A and B is for refolding experiment, and C and D is for unfolding experiment. And the 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 fluorescence signal at t equal to 0 and t equal to infinity is plotted for both urea and guanidinium hydrochloride thing. So A is urea, B is guanidinium hydrochloride, B and D is GD and guanidinium hydrochloride, A and C is the urea thing. And it was seen that in the later part that in the equilibrium experiment, so whatever, let's say A is for the uh, so A is the thing with a melt at 310 nanometer in urea, and what was seen that you know uh, all the uh, t is equal to infinity points. So the so t is equal to infinity points is the kinetic refolding traces. So in t at infinity in refolding will bring the fluorescence signal to which is at the native baseline. And the open circle, these things are t equal to 0. So for the refolding experiment, the this is the for the refolding experiment after at t equal to 0, at t equal to 0 the signal is supposed to be on the native baseline. So what does it indicate? That protein at t equal to 0, protein remains in its native conformation, but because of the effect of urea, uh, 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 the fluorescence increases. So this we know that baselines are nothing but the dependence of fluorescence on the urea concentration. Now, second thing is for the unfolding experiment, these ultra triangles, fill triangles are t is equal to infinity. So as you see that for the unfolding experiment, t at infinity means a protein will be in unfolded conformation. So at different denaturation concentration, it is t equal to infinity means equilibrium, at equilibrium. And this for unfolding experiment, t is 0 means protein will remain on native conformation at t equal to 0, and that's why it is falling on the baselines. But there are other arguments as well, because it is not completely falling on the baselines but going up. So now to explain this, now we'll read here uh, somewhere here. Okay, so figure 3a and b compares kinetic and equilibrium amplitude of fluorescence monitored folding and unfolding in urea as well as in guanidinium hydrochloride. The t equal to infinity and t equal to 0 points of kinetic refolding traces fall on the equilibrium unfolding curve and linearly extrapolated unfolding protein baseline respectively. This indicates that the entire amplitude of refolding reaction from U to N is captured in the kinetic experiment. For both denaturation, the t equal to infinity points of the kinetic unfolding traces fall on the equilibrium unfolding transition, but t equal to 0 points do not fall on the linearly extrapolated native protein baseline as a result of burst phase increase in fluorescence. So as you see that as here as urea concentration increases, yeah, so there are always burst phase. This t equal to 0 would be biased because things are in, and when you have more urea concentration, so essentially this is not at t equal to 0. So here it is okay till here, but now this is, and in case of guanidinium hydrochloride there is a clear transition for unfolding experiment. This is all t equal to 0. So you see that you know the burst phase, because of burst phase it is instead of falling on native baseline, but it is falling on a sigmoidal thing as a result of native burst, as a result of native burst phase means from mixing native protein in urea here and guanidinium hydrochloride here. Essentially the signal changes quickly before we start taking measurements. So that's what is here. But the question is, so for unfolding by guanidinium hydrochloride, the T equal to 0 point show a typical sigmoid dependence on the concentration of denaturants. For unfolding by urea, the sigmoidal dependence could not be established clearly because it was not possible to carry out unfolding experiment in sufficiently high concentration of urea. Now the sigmoid dependence on denaturant concentration of the burst phase amplitude seen for unfolding in guanidinium hydrochloride suggests that the burst phase increase in fluorescence accompanies the initial establishment of free equilibrium between N and an unfolding intermediates I before the subsequent slower unfolding of I to U. So let me repeat it again. The sigmoidal dependence of denaturant concentration dependence on the denaturant concentration of burst phase amplitude seen for unfolding in guanidinium hydrochloride suggests that the burst phase burst phase uh, the burst phase increase in fluorescence accompanies the initial establishment of pre-equilibrium between N and unfolding intermediate I before the subsequent slower unfolding of I to U. Hence, the analysis was carried out to a two-state N to I mechanism in order to determine the value of delta G and I in water and so hence the analysis was carried out to a two-state N2I mechanism in order to determine the value of delta G Ni H2O and MENE. Now the native protein baseline used in this analysis was that obtained for equilibrium unfolding transition. Yeah, because it does not have a native state baseline, because you cannot jump to zero concentration of urea essentially. Yeah, here argument is clear that you cannot jump to 0 molar concentration of urea. So it says that so that's why to address this this change in the sigmoidal change in T equal to 0 for unfolding experiment. So they had to take the baseline by equilibrium experiment, because when you know, for an unfolding measurement you have a native protein and you mix it with unfolded buffer. So in fact you cannot really yeah, you are never at 0 molar or 0 to 1 molar concentration. So so here they have used it, you know, the native protein baseline used in this analysis was that obtained for the equilibrium unfolding transition. The fluorescence properties of I appear to be similar to those U at high concentration of denaturant. In high concentration of guanidinium hydrochloride, the entire increase in fluorescence during unfolding occurs in burst phase. The fluorescence properties of I appear to be similar to those of U at high concentration of denaturant. In high concentration of guanidinium hydrochloride, the entire increase in fluorescence during unfolding occurs in the burst phase. So hence it was assumed that the dependence on denaturant concentration of the fluorescence of I is same as of U, the value, and hence it would consider the 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 unfolded baseline. The values obtained for delta GNI and MENI are 2.1 kilocalorie per mole and 0.48 kilocalorie per mole. So they have used a native and unfolded baseline from equilibrium measurement. So since it's an important point, I'll read it again. So it says, see here. Okay, so since here. So the sigmoidal dependence of denaturant concentration on the burst phase amplitude seen for unfolding in guanidinium hydrochloride suggests that the burst phase increase in fluorescence accompanies the initial establishment of a pre-equilibrium between N and an unfolding intermediate I before the subsequent slower unfolding of I to U. Hence, the analysis was carried according to a two-state N to I mechanism in order to determine the value of delta G N I H2O and MENI. So the native protein baseline used in this analysis was obtained from the for the equilibrium unfolding transition, the fluorescence properties of I appear to be similar to those of U at high concentration of denaturant. In high concentration of guanidinium hydrochloride, the entire increase in fluorescence during unfolding occurs in the burst phase. Hence, it was assumed that dependence on denaturant concentration of fluorescence of I is same as that of U. Now, the value obtained for delta G and I. So, this is the important part. It has assumed that dependence on denaturant concentration of fluorescence I is same as U, and hence will have similar unfolded baseline. So, the value obtained for delta G and H2O is 2.1 kilocalorie per mole, and MENE is 0.48 kilocalorie per mole respectively when urea is used as the denaturant. In the case of guanidinium hydrochloride, the value of delta G and I is 3.7 kilocalorie per mole, and MENI is minus 1.53 kilocalorie per mole. So, you see that in case of urea, it was determined as 2.1 kilocalorie per mole. So, this is the difference between intermediate and the native state. So, this is important that in urea, the difference between native and intermediate state is 2.1 kilocalorie per mole, and M value is 0.48 kilocalorie per mole per molar inverse. Now, in the case of guanidinium hydrochloride, the value of delta G and H2O is 3.7 kilocalorie per mole. In case of okay, so okay, yeah, yes, indeed. And for urea and guanidinium induced unfolding, the observation that the value of M value is less than the value of N to U. So it means I has some structure. So suggesting that unfolding of N to I exposes less surface area than unfolding of N to U. In other words, I is not unfolded to the same extent as U, even though its fluorescence properties appear to be similar that of U. So, in other words, I is not unfolded to the same extent as U, even though its fluorescence property appear to be same as U. Figure 3C, so this one, which is about electricity, compares kinetic and equilibrium amplitude of far UV-CD monitor unfolding in urea. The T is equal to infinity and T is equal to 0 points of the far UV-CD monitored kinetic unfolding traces fall on the equilibrium unfolding curve and the linearly extrapolated native protein baseline respectively, indicating that the entire amplitude of unfolding reaction from N to U is captured in the experiment 3C. Now this one. So we have all the values here, right? So now if we try to understand what happens in the three-state analysis. So figure 1 to 3 shows that unfolding intermediate can be detected under equilibrium condition, and in kinetic studies an unfolding intermediate can be seen to form very rapidly during unfolding. In both cases, the intermediate appears to remain N-like far UV-CD but to have lost N-like fluorescence. While it is possible that two different intermediates are detected in the equilibrium and kinetic studies, the simplest assumption that the intermediates are one and the same in either denaturant. So this assumption is considered this assumption is consistent with using the simplest and minimal model N to I to U that can adequately describe all the kinetic and thermodynamic data. So hence the three-state analysis of the fluorescence and far UV-CD monitored equilibrium unfolding transition, which both describe the equilibrium between N and I and U, was carried out using the value of delta G and H2O and Mi means M value obtained from the analysis of denaturant dependent burst phase change in fluorescence seen in kinetic unfolding experiments. Now, when this was done for both urea and guanidinium hydrochloride induced unfolding, similar values were obtained for stability of N relative to U in either denaturant and Similar values were obtained in both denaturant for alpha 1 I, a measure of position of I on the reaction coordinate relative to U and N based on the degree of solvent accessible surface area. Nevertheless, the true test for the assumptions that the same minimal N to I to U mechanism is adequate to describe both the kinetic and equilibrium data is whether the thermodynamic parameter which was determined from the analysis of the denaturant dependence of the equilibrium amplitudes as well as the kinetic burst phase amplitudes are predicted by and are consistent with the rate constant data. Now the dependence of the observed refolding and unfolding rate constant on denaturant concentration shown in figure 4 were therefore analyzed on the basis of N to I to U mechanism. So the fourth picture. So this is the dependence of the observed unfolding and refolding rate constant on concentration of denaturant. The observed refolding is so the open circle and open triangle is observed refolding, and closed circle and closed things are observed rate constant. We measure in different concentration of guanidinium hydrochloride are a urea-ish triangle by monitoring the change in fluorescence at 300 nanometer. So the continuous lines through the rate constants are fits to sum of equations. For fitting, the value of pre-exponential factor A in equation 10 and 12 was fixed at 10 to the power 6 second inverse, and values of delta G and I, M and I were fixed to the value obtained from two-state analysis of the T is equal to 0 point of kinetic unfolding traces. The values obtained for various parameters are given in table 1. The error bars are represented later. So yes, the same thing. The observation that no burst phase change in fluorescence occurred during folding in any concentration of denaturant suggests that I does not accumulate and that the U to I transition is the rate limiting step of folding in change in the range of denaturant concentration studies. This inference is supported by observation that the folding arm of chevron are linear in both the denaturant. The observation that the burst phase change in fluorescence occurs during unfolding in either denaturant suggested that the rate constant for transition from N to I and for the transition from I to N are much faster than the rate constant from transition from I to U at all concentration of denaturant. So that's why in chevron plot you don't see it, right? Now the dependence of denaturant concentration of the observed folding and unfolding rate constant were fit to sum of equation 10 and 12 in using equation 10 and 12 to obtain value of delta G IU and MIU and delta GUI and MUI. The values fixed for delta GNI and MNI were those obtained from the two-state NI analysis of the denaturant dependence of T equal to 0 points of the kinetic unfolding traces as described above. So the values obtained for the various parameters are given in table 1. Now just see the equation 10 and 12 once again. So 10th equation is this. So yeah, so yes, so it is fitting and giving you things. Okay. So now refolding and unfolding of SS3 domain and urea versus guanidinium hydrochloride. So they have presented the difference. I can quickly go through this, and table 1 compares the values of various thermodynamic and kinetic parameters determined when refolding and unfolding was carried out in guanidinium hydrochloride to those obtained in urea. The values of delta G and U obtained from equilibrium as well as the kinetic studies were similar for both the denaturant. A denaturant dependent burst phase during unfolding was observed for both denaturants. the value obtained for alpha 1, which is a measure of the extent of folding in I, compared to that in N, is similar for folding in both the denaturants. Hence, it appears that the same intermediate I is populated during folding or unfolding in urea and in guanidinium hydrochloride. For folding in sorry. So, for folding in either denaturant, the value of Tanford value for the rate limiting transition is about the same. So, implying that about 50% of the change in solvent accessible surface area during folding has occurred in TS1. So, now the product of the burst phase of unfolding is a partially unfolded species. To determine whether the product of the burst phase during unfolding is partially unfolded form or whether a fraction of the native molecule has unfolded completely, interrupted unfolding experiments were carried out. Figure 5a show, so this is the product of burst phase of unfolding is a partially unfolded species. So, the argument about the intermediate, I guess. So, it says that to determine whether the product of burst phase during the unfolding is partially unfolded form or whether fraction of native molecules has unfolded completely, interrupted unfolding experiments were carried out. So, let us see figure 5a. So, this is figure 5a. So, it is the kinetics formation of U from the N state. Native protein was unfolded in 3 molar guanidinium hydrochloride at pH 7.2 for variable length of time from 276 millisecond to 50 second before refolding was initiated by diluting the concentration of denaturant to 1 molar. Okay. So, number A is representative refolding traces when protein was refolded after unfolding for 50 seconds, 12 seconds, 6 seconds, 3.2 seconds and 1.2 seconds. Each refolding traces was fed to single exponential equation which yield an observed rate constant of refolding 0.028. All kinetic traces were normalized to t is equal to 0 point and refolding traces were unfolding for 50 seconds. So, it says that figure 5a shows representative kinetic refolding traces of protein that had been unfolded, right, for 50 second in 3 molar guanidinium hydrochloride for different lengths of time from 275 millisecond to 50 second and then refolded diluting guanidinium hydrochloride to 1 molar. The t equal to 0 points of the kinetic refolded trace do not fall on directly unfolded trace obtained in 3 molar guanidinium hydrochloride, indicating that there is a burst phase change in fluorescence in addition to the observed phase of fluorescence change during refolding. The 5b, there is a burst phase change in fluorescence. So, what is happening here? So, what is the 5b thing? So, this is like the so top to bottom. This is first unfolded for 50 second, unfolded for 12 second, unfolded for 6.2 second, unfolded from 3.2 second, and then 1.2 second, and after that it went for refolding to by reducing the urea concentration. So, here it is A is so it's a guanidinium hydrochloride, not urea. It's guanidinium hydrochloride. Okay, so and B is a comparison of signal at t equal to 0 points of the kinetic refolding traces after unfolding in 3 molar guanidinium hydrochloride for variable lengths of time with a single jump unfolding trace obtained when protein was unfolded in 3 molar guanidinium hydrochloride. So, yeah, this is it. This is what is this? This is t equal to 0. Yeah, this is the t equal to 0. If I can change the color. So, this is t equal to 0 points. So, at t equal to 0 points kept on increasing as we increase the time of unfolding, right. This is the time of unfolding, yeah, till 50 second. So the protein was unfolded. So and this triangle is t equal to infinity points of the kinetic refolding traces. So of course, after it's refolded, it will have signal like which is close to native. The continuous line through the open triangles is a fit to the single exponential equations which yield observed rate constant of 0.1 second inverse. The single jump unfolding curves was also fit to single exponential equation which yield an observed rate constant for unfolding of 0.1 second inverse. The third is the increase in relative amplitude. Third is the increase in relative amplitude of the observed phase with an increase in the time of unfolding before refolding was initiated. The amplitude of all refolding traces were normalized to amplitude of the refolding curves obtained when the protein was unfolded for 50 seconds before refolding. The fit to a single exponential equation shows the continuous line, right? So now here it says that uh, yeah, so the t is equal to 0 points of the kinetic refolding traces do not fall on direct unfolding traces obtained in 3 molar guanidinium hydrochloride, indicating that there is a burst phase change in fluorescence in addition to the phase of fluorescence change during refolding. So this is t is equal to infinity, right? This is t is equal to no, this is not. So in B, what does B say? B starts from here. The comparison of signal at t equal to 0 points of the kinetic refolding traces obtained after unfolding in 3 molar guanidinium hydrochloride, okay, for variable length of time. So see, this is first unfolding and then refolding. This is the experiment. So first unfolding, this is the t equal to 0 points, and which t equal to 0, this is not t equal to, how can it be t equal to 0 point? This should be 3 molar guanidinium hydrochloride. The t equal to 0 points, and no, it's like that only, and t equal to infinity points of the kinetic refolding traces. So this is t equal to 0 for kinetic refolding traces. Okay, so let's say here they have unfolded for 10 seconds, and after that it is refolding for whatever time is here. So what is the t equal to 0? This value is plotted here. So the value, this value, if you see, this is close to 0.6 or so, no 0.7 say आपको. So this is close to point. So this is the t equal to 0 for refolding experiment. So it is showing it, and this is the t equal to infinity at refolding experiment, which is like this. So it shows what does it say now. Now figure 5a show representative kinetic refolding traces of protein that had been unfolded in 3 molar guanidinium hydrochloride for different lengths of time from 275 millisecond to 50 second, and then refolded by diluting the guanidinium hydrochloride to 1 molar. Now the t equal to 0 points of the kinetic refolding traces do not fall direct on the unfolding traces obtained in 3 molar guanidinium hydrochloride, indicating that there is a burst phase change in fluorescence in addition to the observed phase of fluorescence change during refolding. Now the amplitude of burst phase decreases with an increase in the time of unfolding in 3 molar guanidinium hydrochloride. The observed phase is described well by signal exponential equation. This is similar to the observed rate constant of refolding in 1 molar guanidinium hydrochloride of a completely unfolded protein. Now figure 5c shows figure 5c shows that the relative amplitude of the observed refolding phase increases with an increase in time of prior unfolding in 3 molar guanidinium hydrochloride. The amplitude of the observable phase increases with an observed rate constant of 0.1 second inverse, which is similar to the the directly observed rate constant of unfolding in 3 molar guanidinium hydrochloride. All molecules are found to be completely unfolded when unfolding is interrupted at 50 seconds. The resulting refolding trace does not display a burst phase, and the observable phase has an apparent folding rate constant similar to that seen in a single jumper refolding in 1 molar guanidinium hydrochloride. This indicates that the observable phase of refolding after interrupted unfolding correspond to refolding of a completely unfolded protein U, whose population increases with an increase in time of unfolding. The burst phase of refolding after interrupted unfolding represents the refolding of a partially unfolded forms whose population decreases to 0 with increased time of unfolding. Now the discussion, number 1, the SS3 domain of PI3 kinase is not a two-state folder. So this is quite a big discussion, but we'll read it quickly. So in early study, the folding of SS3 domain of PI3 kinase, the folding reaction appeared to be two-state even when studied by multiple probes including NMR. The study appeared therefore to preclude any significant accumulation of intermediates before the rate limiting step of folding, but it did not preclude the formation of folding intermediates after the rate limiting step. In the same study, no unfolding intermediates was detected, but guanidinium hydrochloride was the only denaturant used in the equilibrium and kinetic studies. It was not used at a concentration greater than 3 molar. Moreover, multiple probes were not used to study unfolding as they were used for studying refolding. The rates constant of data appeared to fulfill kinetic criteria of two-state folding. The extrapolated values of the observed rate constant of folding and unfolding lambda f and lambda u in water predicted the stability delta G and U of the protein. Now the dependence of lambda f and lambda u on guanidinium hydrochloride concentration predicted the dependence on guanidinium hydrochloride concentration of free energy of unfolding delta G and U. And third, the concentration of guanidinium hydrochloride at which lambda f and lambda u had identical values was also the concentration corresponding to the midpoint of the equilibrium unfolding transition. In this study, the observed rate constant of folding and unfolding in guanidinium hydrochloride were identical with those reported earlier, and hence the values for lambda f and lambda u in guanidinium hydrochloride as well as in urea reported here also predict apparent two-state folding. But several observations indicate that the folding and unfolding reaction of SS3 domain is not a two-state but a multi-state. Number 1, the equilibrium urea induced unfolding monitored by fluorescence and far UV-CD are not coincident. So this indicates population of an unfolded intermediate that exists in equilibrium with native and unfolded protein at intermediate concentration. 2, in kinetic studies, a burst phase of fluorescence change is observed during unfolding in either urea or guanidinium hydrochloride at higher concentration of denaturant. And third, a burst phase change of fluorescence is observed during the refolding of transiently unfolded protein. Hence, it is necessary to use minimally a 3-state N to I to U mechanism to analyze the equilibrium and kinetic data. Now, identify the equilibrium and kinetic unfolding intermediates in this study. The equilibrium intermediate has been identified under equilibrium unfolding condition as well as in kinetic unfolding studies. It is shown that 3-state N to I to U model is the simplest and minimal model that can completely describe all aspects of both kinetic and equilibrium data in an internal consistent manner, and that it is not necessary to include any additional intermediate for analysis of all the data. Thermodynamic parameters such as delta G and M describing the model have been determined using the amplitude of signal change seen during equilibrium unfolding in conjunction with amplitudes of signal change seen in kinetic experiments and analyzing the dependence of these amplitudes on denaturant concentration according to the 3-state model. The same thermodynamic parameters are predicted with experimental errors by application of the same three-state model to analyze the rate constant data from kinetic experiments in either denaturants. Hence, the assumptions that kinetic intermediates are identical with those observed under equilibrium condition, which has not been made in case of the folding of the other protein, appears to be valid in this case. Now, the SS3 domain of PI3 kinase has 7 tyrosine residues disappeared throughout its sequence. Hence, observation that the fluorescence of I is the same as that of U indicates that I is solvated throughout its structure, and it is not the case that that only a local segment of structure has become solvent accessible in I. Now, the latter possibility is in fact discounted by the analysis, which indicates from the value obtained for the parameter alpha I that only about 55% of solvent accessible surface area has become buried in I. Now, it should be noted that although the SS3 domain does have a single tryptophan residue in its sequence, this residue is on the surface of protein. If the intrinsic tryptophan fluorescence is used to probe unfolding, a very small apparently non-cooperative transition is observed. If intrinsic tryptophan fluorescence is used to probe for unfolding, a very small apparently non-cooperative transition is observed. So, the SS3 domain of PI3 kinase has 7 residues, tyrosine residues, and since I and U has similar fluorescence at 300 nanometer, it indicates that I is solvated throughout its structure, and it is not the case that only a local segment of structure has become solvent accessible in I. The latter possibility is in fact discounted by the analysis, which indicates from the value obtained for the parameter alpha I that only about 55% of solvent accessible surface area has become buried in I. It should be noted that here that although the SS3 domain does have a single tryptophan residue in its sequence, the residue is on the surface of the protein. If the intrinsic tryptophan fluorescence is used to probe the unfolding, a very small apparently non-cooperative transition is observed. Now, nature of burst phase product. Burst phase change during protein unfolding have been reported for several proteins. The burst phase change can arise due to accumulation of partially unfolded conformations. Now, in few cases, however, like that of canine milk lysozyme, the burst phase change arises due to fraction of the native protein molecules unfolding very fast when there is a heterogeneity in native state. The burst phase change in fluorescence observed during both the urea and guanidinium hydrochloride induced unfolding of SS3 domain of PI3 kinase has been interpreted to signify the very fast formation of an intermediate I and not the formation of U. This is because a two-state analysis of burst phase amplitude indicates that the burst phase represents the unfolding of N2 a form whose solvent accessible surface area is only about 45% of U. So, it should be noted that because I formed at least 100 times faster than U over the entire range of denaturant concentration studied, it was possible to consider a pre-equilibrium between N and I for analysis of kinetic data. Now, heterogeneity in the native state has been reported for the alpha spectrine SS3 domain. Partial unfolding manifested as EX1 exchange has been observed for many SS3 domain when studied by hydrogen deuterium exchange coupled to mass spectrometry. In the case of the SS3 domain of PI3 kinase, it seems very unlikely that the burst phase change in fluorescence arises due to conversion of native state to native like state, because there is a significant change in solvent accessible surface area is going from native state to burst phase product. Now, the intermediate I is therefore not a native like structure, even though its secondary structure as indicated by far UVCD at 222 nanometer appears to be same as N. Now, in interrupted unfolding experiment, a different species populated during unfolding can be distinguished by their rates of refolding. At 276 millisecond of unfolding, when mostly the burst phase product is populated and no significant fraction of molecules is completely unfolded, the time constant of unfolding is 10 seconds. A refolding trace with maximum burst phase amplitude, uh, a refolding tax, you know, um, so this so at 276 millisecond of unfolding, when mostly burst phase product is populated and no significant fraction of molecules is completely unfolded, the time constant of unfolding is 10 seconds. A refolding trace with maximum burst phase amplitude and no significant amplitude for the observable phase is observed. This implies that the species populated at the end of burst phase refold much faster within the 11 millisecond dead time than does the completely unfolded protein. This is direct evidence that the product of the burst phase during unfolding of SS3 domain is a partially unfolded conformation. Now, the initial accumulation of intermediate I during unfolding, which results in a burst phase change in fluorescence, is also seen uh, to lead a downward curvature in the unfolding arm of chevron plot for either denaturant uh, as predicted by equation 9. Such curvature is been unfolded branches of chevron plot has been seen also in unfolding studies of the protein, where they have been attributed to the presence of high energy intermediates. Now, the mechanism of unfolding: the observation of three state N, I and U and two steps burst phase and observable phase during the unfolding of SS3 can be explained by the minimal mechanism N to I to U. This mechanism account for equilibrium unfolding data and the kinetic unfolding data. During unfolding, a pre-equilibrium is established between N and I. During unfolding, a pre-equilibrium is established between N and I. During unfolding, a pre-equilibrium is established between N and I in the burst phase, and this equilibrium shifts towards I with an increase in denatured concentration. Now, from single jump unfolding experiment, it appears that the fluorescence of I is similar to U. Now, thus the change in fluorescence takes place when N unfolds to I, while I to U transition is silent to the fluorescence. Now, the observable change in fluorescence during unfolding arises only because of the slow I to U transition. Okay, so the observable change in fluorescence during unfolding arises only because of slow I to U transition perturbs N to I pre-equilibrium such that more N molecules are pulled towards I. In 3.5 molar guanidinium hydrochloride, the equilibrium constant KNI for the N to I pre-equilibrium is high and all the N molecules unfold to I during the burst phase itself. Hence, no observable phase is observed. In interrupted unfolding experiment, the amplitude of the observable phase of the refolding trace appears to increase at the expense of burst phase amplitude, which suggests that I unfolds directly to U. The alternative three-state mechanism I to N to U, in which I is an off-pathway intermediate. According to this mechanism, a pre-equilibrium is established between N and I. So here you see N and I, and here's the U. Okay, they are transition state 2, transition state 1, and the protein molecules in its native state unfolds directly to U in the observable phase. In the three-state analysis, the urea induced equilibrium unfolding experiment, um, according to A to B to C mechanism, the M value indicate that B has a solvent accessible surface area intermediate between those A and C. Hence, it is unlikely that B corresponds to N. Nevertheless, it is impossible to conclude any only from equilibrium unfolding experiments whether an intermediate is on pathway or off pathway. So, let us see this. So, formation of an intermediate during the refolding and unfolding of SS3 domain of PI3 kinase. A is the free energy profile in the absence of guanidinium hydrochloride. A partially folded species is formed after, and B is the free energy profile for unfolding in 4 molar. So, that is why in 4 molar guanidinium hydrochloride U is more stabilized. Yeah, something like that. So, the SS3 domain of PI3 kinase contain 3 proline residues also. Oh, quite a long. Okay. So, um, 3 proline residues also, and they are in trans conformation in the native protein. It has been suggested that about 30% of unfolded protein molecules have proline 69 in its cis conformation. It should be noted, however, that the observed unfolding of SS3 domain into kinetic phases cannot be explained by N to U2 to UC mechanism, in which UT and UC are two completely unfolded forms uh, with the phenylalanine 68, proline 69 peptide bond is the native trans conformation and non-native cis conformation respectively. In such a mechanism, N would unfold to UT very rapidly during the burst phase, and UT to UC transition is prolyl peptide isomerization reaction. That would give rise to the observable phase. Such a mechanism is unlikely because number one, the observed unfolding rate constant have a steep dependence on denaturant concentration, which is not expected for prolyl peptide bond isomerization reaction. The observed rate constant are also faster than expected for a prolyl residue peptide bond isomerization reaction. And 3, all the changes in solvent accessible surface area would take place from N to UT, but only about 45% of surface area change occurs from N to the burst phase product. Now, the characterization and position of the rate limiting transition state of the folding. So, that can be studied. Validation of population of an intermediate after rate limiting step of folding in guanidinium hydrochloride. So, essentially the take home message is the protein shows sort of protein shows the it unfolds and refolds in 3-state manner. Now we need to connect it with what happens when monitored at different wavelength.